All right. So as we start our field trip today, I want to remind you of the 3 different rock types that we're going to be seeing as we wander around campus. There's igneous rocks, there's sedimentary rocks, and there's metamorphic rocks. And you'll remember that igneous rocks are formed from molten rock, so magma or lava if it comes out onto the surface. And sedimentary rocks are made out of broken pieces of other rocks. Those are the clastic sedimentary rocks, and you'll remember that we also have chemical sedimentary rocks. Those are formed because of the chemical formations that happen in oceans and in lake beds and things like that. And then third, we have metamorphic rocks. Metamorphic rocks are when you take pressure and heat and a lot of time and you squish those other previously made rocks, and in a solid state, they change and become metamorphic rocks. And so we're going to actually see all 3 of these types of rocks as we wander around campus today. The Eyring Science Center has a lot of displays set up to help you see some of the characteristics of some of these different types of rocks that we've talked about. For example, this one here is a gneiss. This was quarried in Brazil and was given to us by some furniture makers. This looks, not furniture makers, countertop makers. This looks a lot like some of the, maybe the granite countertops that you have in your home or that you've seen around. However, it's not even a granite, it's a gneiss. And we know that it's a gneiss because we can see the banding. It has the gneissic banding. And this is one of the key ways that you can tell what a gneiss is these layers of, these compositional layers. All of these dark minerals have been clumped together, and then we have light minerals that have been clumped together, and then we have dark minerals. The minerals that we see, we're seeing pink minerals, we're seeing white minerals, we're seeing black minerals, and we've talked about each of these types. The pink minerals are feldspars, as are the white ones. The darker colored ones are amphiboles and biotites and perhaps pyroxenes. They are the mafic minerals, whereas the lighter colored ones, the plagioclase, the potassium feldspar, and the quartz, those are the felsic minerals, more on the felsic range. And you can see that as you add that pressure and time and that heat, we actually were able, these minerals were able to clump together and get to the ones that they were most alike. And that's what makes these streams this gneissic banding. We're still here on the 3rd floor of the Eyring Science Center. And this is another large slab of polished rock that was given to us by a countermaking company. And if you look at it, you can see that it also has the banding that we were looking at in the other rock, but it's a little harder to see. It's not as obvious. However, this is also a gneiss. Even though it has a very different color, set of colors to it, it is still a gneiss. And you can tell that because of the gneissic banding. One of the fun things about this is that it has garnets inside of it. And all of these little red spots along in here are garnets. And many people who have granite countertops will actually have these little red specks, and they don't even realize that it's a gemstone, it's garnet. And again, this is when you take, say, a sedimentary rock and you add heat and pressure and a lot of time, some chemically active fluids, all the stuff that we talked about with metamorphic rocks. And this is the end result. And keep in mind that this never melts. This is always done in a solid state. Many of the buildings on campus were first built in the 1960s and 70s at a time when the building stone called terrazzo was used quite heavily. Terrazzo is a man-made stone where you actually put a thin base of concrete or cement down, probably cement down, and then you actually add little tiny broken pieces of something, rock, glass, anything that's sturdy, and then you put a polish on top of that. So that's what this floor is. This green speckled rock isn't actually a rock. It's a manufactured building material that actually wears very well. And you can see in places in the Eyring, in the library, and other places around campus where so many people have walked up and down the stairs or have swiveled in a particular area, they actually get a divot in the terrazzo. And that's just from the wear and tear of decades of students wandering around these buildings. We are in the staircases that are right below the geology department in the Eyring Science Center. These staircases are faced with this grayish stone. And I'd like you to look at it and try to decide what kind of stone do you think it is. Is this an igneous rock? Is this a metamorphic rock? Or is this a sedimentary rock? As you're looking, try to keep in mind the types of things that might indicate which one it was. For example, if you see, for example, a seashell in it, then it's going to be a sedimentary rock. But if you see a large crystal in it, you would start to wonder if it was an igneous or a metamorphic rock. In this case, if you decided that this was a sedimentary rock, you are correct. It's actually been put on its side. So you need to actually rotate it 90 degrees to think about the way it was formed. It has these layers, and these layers were actually horizontal. But for the interest of beauty and making this look nice, they've rotated them 90 degrees. Each of these layers is showing you a slight difference in the chemical composition of this rock. This rock is a shale. It has tiny fossils in it, which are these little tiny commas, or maybe some people think they look like eyelashes. And these little tiny shells actually were from a creature that died up in the water table above it and floated down through the water and settled on the ocean or the lake floor. And that is how we know. And we can actually tell which direction was up, because as they were floating down, more often they're going to float down so that they are smiles instead of frowns. And you can actually then, in your mind, rotate this to be the correct direction. And you can see that each of these little smiles is pointing up. This one is a little bit off. So that was just a case where something disturbed it or something, and it got pushed the other direction. In these stairwells, this part of the stair rail actually gets cleaned quite often. And sometimes caustic materials are used for cleaning it, especially right now as we're going through COVID. We need to make sure the high-touch surfaces are always clean. The problem with this is this particular shale is not very sturdy. And it actually reacts really, really badly when different cleaning materials are actually dripped upon it and then not wiped away quickly enough. And so you will see this up and down these stair rails. You'll actually see where the cleaning has happened. Here we are on the west stairs of the Eyring Science Center. These stairs are made out of stone, and I want you to take a good look at it and actually try to figure out what kind of stone you might expect this to be. Is it igneous? Is it metamorphic? Is it sedimentary? Have we seen something similar to this in any of our other pictures that we've seen from around campus? As you are looking at this, please make sure that you're noticing which types of minerals you see. You see some pink minerals. You see some clear minerals. You see some dark brown minerals or black minerals. You also may see on some of the steps these bands. And as soon as I say the word bands, you should automatically think of a particular type of rock. Remember, gneissic banding. These are gneisses. So this staircase is really nice. I told you there's a lot of really bad puns in geology. Sorry. But you can see that they're not as banded as some of the other pieces that we looked at that were on the walls of the Eyring Science Center. But this still has just faint areas where you can see that it has gneissic banding. Again, we're seeing the same minerals. We're seeing the feldspars, that's the pink and the white. We're seeing the quartz, that's the gray. And we're seeing the dark colored ones. Those are the mafic ones, the biotite, the amphibole, and the pyroxene. And that is we're going to keep seeing those. So hopefully you'll start to recognize them. All throughout campus, we have our building name rocks. And these are sort of like little tombstones that tell you where you are on campus. Right here, we're at the Ezra Taft Benson building, which is the chemistry building, but any of these, they're all made out of the same kind of rock. So if you are here, go ahead and pause the video and take a really good look at what this is made out of. So as you are looking at it, I'm hoping you're noticing that it has some white minerals, some gray minerals, and some black minerals. Those should be familiar names and colors to you. because we are seeing those all over. Once again, the white ones are feldspars, the gray ones are quartzes, and the black ones are mafic mineral, either amphibole or biotite. This is a granite. All over campus, we have these gorgeous stones of granite. They've been carved, and as they've been carved, they've actually had some stuff put in so that they look darker. And so I think they have to come around and actually fix that up sometimes, because it's not part of the natural stone, so that you can actually see the namings of it. But granite is a great choice for this type of a thing. It's very sturdy. You can spray water on it and it's not going to really change a lot. And so these should stand the test of time, and we should always be able to see which buildings we're at. Here we are in front of the Joseph Smith building, and there is this peculiar, large, round stone. It's very beautifully rounded. You can tell that it was not done by anything like very modern. It's very bumpy, but to have this type of really great spherical shape is kind of impressive. This is from Costa Rica. It's called the Costa Rican stone ball. Really descriptive there. What it is it's made out of granodiorite. Remember, the granite is just a compositional name for intrusive igneous rocks. And a granodiorite is telling you that it's headed towards the dioritic edge. So it's getting a little bit more mafic, but it's not all the way into that. So they call it a granodiorite. You can actually see different types of minerals. You can see these gorgeous amphibole, these long, skinny, gorgeous black amphiboles. That's one of the mafic minerals. The lighter stuff in between that's looking all rusted because it's been out and exposed to the elements for hundreds and hundreds of years are some of the feldspars and the quartzes. Now this big, huge granodiorite ball was actually carved by pre-Columbian people in Costa Rica between 200 and I think 400 or 500 years AD. So this is during the time of the Nephites, or right around in that time. And so who knows if the Nephites really were in Costa Rica or not, but this is from the same time period as they're having all of their final wars, and Mormon is fighting and Moroni is, finishing things up. And the neat thing about this is that we actually don't know what it was for. This is, they think it's either for a boundary marker to say, hey, this is the end of your boundary, this is the beginning of my boundary. It could also be a gravestone of some kind. It also could have been used for some astronomical work that the native people in that area used to be able to do. Regardless of that, it's pretty impressive that they were able to carve this giant, massive stone using hand tools. And that's it, and make it so spherical. The Joseph F. Smith building on campus is faced with this gorgeous kind of cream-colored stone. Take a good look at it and try to decide what kind of rock would you think that this is. Some things to notice as you're looking. You can see some layers to it. You can also see some little tiny holes inside of it. And as you look at it, you can see that each one of these has those same characteristics. What we're looking at here is we're looking at a travertine. Travertine is a chemical sedimentary rock. It's laid down by little tiny bits of limestone that rain down from, it's usually found in oceans or in other types of water. It's an underwater formation, generally speaking. And this particular travertine is a limestone that was probably created in shallow, warm seas. And you can see the different little layers as the different layers were precipitated. That means they come out of solution and actually make a solid in long, long, long layers, which helps you understand that it's a sedimentary rock. On the west side of the library, there's this alcove that has a plaza in it. And if you come in here and you look at the planter boxes, you can actually see one of the prettiest rocks that we have on campus. This is a granite. But this granite isn't just any type of granite. It's got very large grains. The size of each of these phenocrysts, which of course is what we call the large mineral grains in igneous rocks, is really impressive. And then it has smaller ones in between. You can actually see the potassium feldspar, the pinkish type of mineral. And right next to it, right here, we have a plagioclase feldspar. And surrounding it, we have lots of little tiny amphiboles, the mafic dark mineral. And this is just this beautiful granite that then also has these rather interesting little clumps of dark minerals. The Salt Lake Temple also has these types of clumps. And if you've ever looked at the Salt Lake Temple, you can actually see these big black blobs on it. Those aren't flaws in the stone. They're actually part of the stone. They're called Schlehren. Schlehren, it's a German word, and it is talking about these it's when in the rock body that became this granite as it cooled, there was actually some convection going on in this great big batholith. And in this batholith, or this pluton, the darker materials, the darker minerals actually got to clump together, and then they get kind of smeared out. So they're usually long and skinny, kind of roundish shaped. And as you look at this, you can actually see a bit of some of the geologic principles, of the principles of geologic time that we've talked about in class. If you look here, you can actually see some cross-cutting relationships. Which happened first, the Schlehren or this vein that cuts through the Schlehren? And if you remember from our discussion about geologic time and relative dating techniques, we know that the Schlehren was there and that at some point later, this cross-cutting vein came through it, because the thing that is there, the thing that is that cuts across it, is actually always going to be younger. On the west side of the library, and actually all along the northern half of the library, both on the west and the east sides, you have these planters that are made out of two different types of a reddish grayish stone. So take a minute, get a good look at them, and try to decide what you're seeing. Things to consider is the luster of the stone, whether you can see a grain size of the stone. How do these two stones, the ones that make up the wall and the ones that make up the cap, how do they compare to each other? Once you've had a chance to consider that, let's talk about what we're seeing. The capstones are sandstone. They're the type of thing that you see down in Zion National Park, Arches, all throughout the southern part of the state. There is so much sandstone. And this sandstone is from giant sand dunes. The sandstone down in the south is from giant sand dunes. Think of the Sahara Desert. That's where we get those giant sandstone cliffs. It's because sand dunes were then solidified and buried, and now they've been uncovered, and that's what we see. In this case, these could be from sand dunes. They also could be from riverbeds. This top stone here, this sandstone. You also get sandstone from riverbeds, where there's a lot of sand being laid down throughout time. You can see the layering in these sandstones. And if you get up close to it, you can actually see the grain size. You can tell that it's made out of little tiny grains. I'm not sure how well we can see it on the camera, but if you go up and look at it, you'll be able to see the grains. You also can see some interesting ripples in the way that it is, in the way that the top looks. And those are probably from distinct events where you're actually seeing the ripple marks in the sandstone. There's a particularly good one here on the end. And you can see the ripple marks. So these were the ripple marks that were actually in the sand before it got solidified. And that is a remnant fabric that we see. Now, let's look at the stuff that's below it. The stuff that's below it isn't the same, but it actually has a lot of similarities. What we see here is we actually have metamorphic sandstone. And what do we call metamorphic sandstone? Quartzite. We've talked about this in class. When you take sandstone and you add heat and pressure and chemically active fluids and time, you actually end up getting this quartzite. And this is made out of sandstone that probably looked a lot like the top part, but has had that extra metamorphism happen to it. And we know that this is metamorphic because, first of all, it's smoother. If you feel, it's quite a bit smoother. It's shinier. It has more luster. And if you look at the grains, you actually can't see individual grains. You actually see crystals that have grown together. And so what's happened is the sand grains that are in the sandstone have actually undergone a change and have become crystals that are bound together not by cement like in the sandstone, but actually because their crystal faces have grown together. So we have quartzite here, and we have sandstone here, and basically what's happened between here and here was a lot of heat, pressure, and time. Right by the library's atrium entrance, we have another large planter, and it is capped with a granite, just like the ones that were in that little alcove in the plaza that we just looked at. But as you look at this granite, it's different. First of all, it's not as pretty, in my opinion. But also, you can see that you're seeing different types. You're seeing different sizes. You're not seeing as much of the black. The Schlieren, which still exist, are much smaller. And it's not as a distinctive looking rock. This granite is still quite beautiful, and you can see that it has fairly large grain sizes. Remember, when you have two different types of grain sizes, so you have the big grain sizes and then you have the little grain sizes, that means that there were two different periods of cooling as this rock solidified. As the rock solidified, perhaps it solidified very slowly at first to allow you to get these big minerals, and then more quickly solidified to get the smaller ones because of something that was happening around the Pluton while it was cooling. So looking at the grain size can tell you a little bit about the conditions under which the igneous rock was cooling and changing. Here in the atrium entrance to the library, as we look down at the tiles that we can see on the floor, we see a lot of the colors that we're used to have seen before. We see the black minerals, we see the light minerals, we see the pinkish minerals, we see a leaf. Anyway, what kind of rock is this? We've seen it before. It looked a little different, but I'm going to let you think for a second. So this is a gneiss, and you can see the gneissic banding. You can see the way the dark minerals have moved together, and you can see how the lighter minerals have clumped together into this nice gneissic banding. Gneissic banding. Nice, Corinne. Remember that we saw gneiss on the steps outside of the Eyring Science Center, and yet those were large slabs of gneiss, and these are little tiles. However, they're both the same type of metamorphic rock. When this building was dedicated, I was a student here 20-something years ago when the new part of this was dedicated, and President Bateman mentioned the marbled granite stairs, and every geologist went, "Oh, marbled granite." Marble is a metamorphic rock, granite is a igneous rock, and he's right that it's a granite that's been metamorphosed, but it has nothing to do with marble. And so that always made us chuckle that he described it that way, but it's not a terrible way to describe it. Marble, being another metamorphic rock, is going to have banding as well. It's not considered gneissic banding because it's not a gneiss, but it does have that same distinctive banding. The minerals we've seen over and over again are quartz, feldspars, and the mafic minerals, amphibole, pyroxene, biotite. As you look at the floor of the atrium of the library, you can see these large white minerals. This is one complete mineral. And you can feel it as you run your finger across it. It's a divot wherever this is. So the way they polish this got polished more. This one doesn't do the same thing, but they're both the same type of mineral. These are feldspars. Right near the help desk on the 3rd floor of the library, just as you come in through the atrium, you can actually, on either side of this area, are 2 huge sculptures made out of stone. And as you look at this stone, I want you to put up your nose next to it. Get right up your masked nose right up next to it and really take a look at it. And then pause the video and try to determine what minerals you see, and then give me an idea about what rock this is. All right, did you figure that out? Hopefully you paused and you did that. You're seeing the same minerals. We're seeing that pinkish mineral. We're seeing the dark minerals. We're seeing the white minerals and the glassy minerals. So the glassy minerals are quartz, and the pink ones are feldspars. The white ones are feldspars, and the black ones are the mafic minerals. However, this particular stone hasn't been metamorphosed. It hasn't had that heat and that time and those chemically active fluids with the pressure. And you don't see the banding. what you do see are some gorgeous little flashes of light. Here's a flash of light right here, one here, one here. Those are individual minerals that haven't been metamorphosed and squashed and stuck together. These grew out of a molten rock, and because they are from a molten rock, this is a granite. This is the same type of granite that was probably heated and pressurized to make the floor that I'm standing on right now. And so if you consider that actually all you have, the difference is you have this particular granite that was created, and then heat and pressure and time heated up this maybe same type of granite. It's probably not the exact same type of granite, but the same general kind. And it created this gorgeous banded stuff that we see below. It's the same minerals. It's the same chemistry. It's just a very different form because of the metamorphism. Here we are, halfway between the third floor and the second floor in the library, the middle set of stairs in the older part of the library. And you can kind of see that it's older. We're standing on the terrazzo. It's not green terrazzo like it is in the Eyring Science Center, but it is still terrazzo. You can see how worn it is. This terrazzo has been around since the library was built in 1976, which, by the way, is older than me. Anyway, this particular stairwell is one of the neatest places on campus to me. And it is because it is made out of these gorgeous rocks that tell you so many things if you just stand here and look at them. So what I want you to do is I want you to pause, and I want you to just look at these rocks and just see how many different types you see. These rocks, though this rock looks so different than this rock, which looks so different than this rock, that looks so different than this rock, actually all came from the same deposit of rocks. And I don't know where they came from, but I do know that they're all related because we can kind of see some of related, some similarities between them. But the thing to realize about these big tiles that are on the wall is that they're actually man-made tiles with big rocks that aren't man-made. So this rock is a natural rock, but this stuff around it is actually cement. And then this rock is not man-made, but the stuff around it. So what they did is they actually created this by placing all of these chunks of rock in cement and then shearing it off and polishing it and putting it up here. Now, isn't that a funny thing to do? But look at how beautiful it looks. So we've seen something that looks like this before. Think back to when we were standing at the corner of the JFSB, and we were looking at that pale yellowy stone that had had layers and looked very kind of delicate, like lacy almost. Well, that was, if you'll remember, was a travertine. It was a sedimentary rock. This also is a travertine, a sedimentary rock, only it's vastly different looking and quite dramatic. But what we see here is we see layer upon layer of calcite. Remember, calcite is one of the most common minerals on the face of the earth, and it mostly forms in water. And what happened in this particular circumstance is if you've ever been to a cave like Carlsbad Caverns or Timpanogos Cave or Mammoth Cave in Kentucky, you've seen stalactites and stalagmites and big old massive things in those caves that were made out of layer upon layer upon layer of calcite. What we call those stalactites and stalagmites is travertine. And this is actually travertine that was actually made from a cave that filled up all the way. So when you walk through a cave like in Carlsbad, you're actually walking through empty spots. And you see places where there's giant stalagmites or something like that, but it hasn't filled up the whole cave. But if the process continues, it will fill up the whole cave. And then you can't walk through it anymore, and you can't see the individual stalactites and stalagmites. And so what happened is somebody found a deposit that looked like this, took it apart, maybe, kind of cracked it all apart with dynamite, who knows what, and actually thought, these are so pretty, let's display them in some way on the wall. And so if you look at this one in particular right here, I'm here in the corner, can you see that this used to be a stalactite or stalagmite here, and there was another one here, and another one here, and eventually they all grew together. These other pieces that we're seeing that are next to it actually have smaller pieces of this in here. And so this particular cave, so it was a cave, and then it got filled in with all of the calcite, with the stalactites and stalagmites, and then it looks like it had a bunch of tectonic activity that broke it up into what we call a breccia. And you'll remember, or we'll talk about breccias when we talk about sedimentary rocks, and those are the big angular rocks. And so you can actually see the bits and pieces of angular rock that actually got embedded inside of the stalactites and stalagmites, maybe while they were still being formed. This is just an endlessly beautiful place to come and look. As we're finishing up this field trip, this sort of field trip, I want you guys to kind of pay attention to the things that are around you. We are lucky to live at the foot of the Wasatch Mountain Range. From campus, you can look to the east and see rocks as old as 540 million years. That's in the Cambrian. Those are the orange rocks that are right below the Y. As you look above the Y, you can also see gray cliffs, which is limestone from the Mississippian age, which is about 330 million years old. These limestone rocks were deposited in a shallow ocean, much like the Caribbean Ocean looks today. These mountains and the valleys we live in were created by earthquakes, and the canyons were created by erosion, by streams and creeks and rivers. As you continue to learn amazing things about geology in class, be sure to take some time to look up at the mountains and marvel at the beauty that God has created for us. Thanks so much for accompanying me on this field trip.